So we've talked a lot about fact analysis, and I want to wrap up the rest of it so to give you an idea, at least very briefly, sort of how this stuff works and is applied, with the idea that most of what you're going to do is going to be as an application through SPSS and that kind of stuff. So I'm not expecting you're going to do this stuff by hand. So as an example, we're going to talk about PCA because, as I mentioned, PCA is sort of a one-shot deal. You do the process, it spits out the results, and you're done. With fact analysis, we'd have to iterate through the stuff. So to save the time of sort of going through that process, we're going to stick to PCA, and with the idea that you would do that again and continue going if you were doing something with a factor analysis process like principal axis factoring or something like that. Okay, so here's an example from the textbook. All right, you got 5 skiers, so it's a tiny data set, so we can't expect a whole lot out of this, but it's a tiny data set with 5 respondents. They responded to 4 questions. How they rated, they went skiing. How did they rate the cost of the ski trip, the lift at the ski resort, the depth, and the depth of the snow, and how powdery the snow was? Those are basically the 4 questions, and they rated those. So this is the data sort of as we collect it, right? So the data as we collect it is in, as the respondent sort of answering questions. It's sort of typical for how we collect data, right? But this isn't the data that is going to be factor analyzed. We're going to convert this over to a correlation matrix. So with PCA, the matrix that is getting analyzed is the matrix we're used to seeing as a correlation matrix. It has these sort of ones down the diagonal here, right? So that's normal for correlation matrix. And remember, factor analysis is trying to reduce data down. It's trying to reduce data so that patterns of correlations and things can be identified. With this particular data set, the patterns are actually fairly straightforward. It's fairly clear. If you look at the correlation matrix, most of the correlations in this matrix are actually really small, except for 2. There's one correlation here that is between cost and lift, right? So it's lift with cost this way, right? So cost and lift has a strong correlation, and that correlation gets repeated here. So again, remember, everything on the below the diagonal and above the diagonal sort of repeat. So let's look at the lower diagonal here. The other large correlation is here between powder and depth. Okay, so powder and depth. So it looks like there are large correlations between cost and lift, and another between depth and powder. So there's likely, because there's these 2 large correlations, there's going to be 2 possible factors that are going to try and explain the pattern. Now this pattern is not very complex. It's just 2 correlations that are large. But let's take a simple example as a way of understanding what's going on, and then we can apply it to more complex things. Okay, so there's 2 correlations. We want to notice principal components identify those 2 correlations and actually create a factor, 2 factors around that. So the way this works, you apply the eigenvalue, eigenvector deconstruction. And so this L matrix are all the eigenvalues, and these are the eigenvectors. This vector put out into space in the units of a correlation matrix, right? These are like, these are put out into space, explains that number of units. How many units are there possible? Well, each item provides 1 unit of variance. So there are 4 total units of variance in this particular data set. 4 variables, 4 units of variance. So the maximum we're going to be able to extract is 4. We can come back with 4 factors, but it's pretty boring. So we're going to try to explain these correlations with something less than 4, hopefully in this case 2, if what I'm saying is my prediction is correct, that we have 1 large correlation there, 1 correlation there. It's likely to come back with 2, identify those 2 separate patterns. Okay. So we do this eigenvalue, eigenvector deconstruction, and we get back that the first eigenvector, this one, explains 2 units roughly of data. This one explains slightly less than 2. This one explains and far less and even far less, right? So it looks like if we're going based on, like we talked about in the lab, that we want eigenvalues over 1, well, we would retain this and this. If we retained all of them, if we kept all 4 of them, we'd be able to reproduce the correlation matrix perfectly. But if we drop these 2 out, we want to see how close are we going to be able to reproduce the correlation matrix as close as possible with only using 2 vectors along with their variances, their eigenvalues. This represents the amount of units of variance explained by the first vector. This is the amount of variance explained by the second vector, and so on and so forth. Okay, so the way this works, we saw this before. I'll just sort of repeat that the eigenvalues can be found by taking the vectors, the transpose of the vector times the correlation matrix times the vector again. All right, so L is the eigenvalue matrix, V is the eigenvector matrix. This is a diagonalized form of the R matrix and reorganized variances in the eigenvalues. There's a lot of details there. The main thing I want to get here is that we're going to use the 4x4 matrix can be summarized by 4 numbers instead of 16. It's basically we're taking the 4x4 matrix and trying to explain it with just 4 sort of eigenvalues along with their vectors and trying to break up the correlation matrix into smaller chunks. All right, so I'm not expecting you to be able to do this or to compute this or any of that kind of stuff. It's just explaining where this comes from. So we have the eigenvalues, eigenvectors, which are sort of it's just the numbers being reorganized in a different way so that we can actually separate out information and try to reduce it down. Okay, so we can reproduce the correlation matrix by taking the eigenvectors times the eigenvalues and then times the eigenvectors transposed again. So VLV will then perfectly reproduce the correlation matrix. If we keep all the eigenvectors, all the eigenvalues, in this case 4, this would exactly reproduce the R matrix, and there'd be 0 between. The residual matrix would be 0. There'd be no difference between the 2 of them. And if we had a chance, I could actually show this, but I'm not going to go into this because we don't have time. I don't want to spend too much time going through a lot of this stuff because this is basically it. It's the end of the semester. I'm doing this as a supplemental lecture. I don't want to make it too long. All right, so there's actually some, if you're interested, I can send you this sort of, this matrix output and you can play around with it. It actually probably is already available to you in this lab or as part of the syntax, and you can play around with it if you like, but if not, it's okay. It gets pretty close. So when we do this, it actually gets pretty close. And if we actually just retain the eigenvalues larger than 1, it actually still gets pretty close, even if we ignore the eigenvectors and eigenvalues related to the third and fourth ones. Just retain the 2 largest ones. We can actually get really close, and the residual matrix isn't perfectly 0, but it's really close, and the values are really small, which means we're actually reproducing the matrix pretty well. All right, so since this is sort of where the computation for loadings come from, since we can reproduce the R matrix, right, by multiplying V times the eigenvectors times the values times the vectors transpose, we can break that up. So since the eigenvectors times the eigenvalues, which are here, times the transpose vector is the R matrix, we can actually split them up. So we actually take the L and so split it in half and make it 2 square roots. So V times the square root of L times the square root of L times the V transpose would be the same thing. It's sort of just rewriting this. We can break those pieces apart if we say that, okay, so the vector times the square root of the loadings, so the square root of the eigenvalues is a loading. That's actually how we can calculate the loading. The eigenvector times the square root of the eigenvalues will give you the loading matrix. That means that V times the square root of L then would define a loading. And that R really is, we can actually reproduce R by taking the loading matrix times the loading matrix transposed would then reproduce R. This is nothing new and nothing to be concerned about. Don't worry about all this stuff. The idea is that the takeaway from this is the loadings really can be computed from the vectors and their values, corresponding values, and then we can actually use the loadings multiplied by itself as a transpose to reproduce R. Now we already saw this. I mean, I didn't say it with equations, but we were looking back at, this is actually quite a while ago, looking back at those matrices that I first introduced to you way back here on slide 16 in this sort of lecture. We said that if I take the factor loading matrix, multiply it by its transpose, I can reproduce the correlation matrix, right? Loadings times the transpose of the loadings give you the reproduced matrix. So all that slide that we're just looking at is saying, it's just showing you that in sort of matrix, or in, you know, using the letters to correspond to the matrices. So it's nothing new. We've already sort of discussed that, and just sort of putting it into play here, that the R matrix is just the loading matrix times its transpose. Okay. If you retain all of the vectors and values, then this will perfectly reproduce the R matrix. If you retain fewer values, fewer vectors and values, this will give you the reproduced matrix that won't be exactly the same, and you can subtract the original matrix and the reproduced matrix to get a residual matrix to see where the differences lie. Larger numbers in the residual matrix indicate that there's parts of the correlation matrix that you're not recovering very well, you're not reproducing. Okay. Again, there's some syntax in there that you can actually go through if you'd like, but I'm not going to go through it now. So when we actually do this, when we actually do the problem, we can actually take this matrix, these two matrices, the L and V matrices, right? We can actually take these, and we can manipulate them into giving us the loadings. Okay, we can take V times the square root of each L, and we're only retaining the first two. So we retain those first two vectors, those that have values over 1. And we can then compute the V times the square root of L to get us this is the unrotated sort of original extracted factors, factor 1 and factor 2. Now we can look at this, and this actually is fairly straightforward, more or less. So what you got is you got two large loadings here on factor 1 for depth and powder. You got two large loadings for cost and lift on factor 2, but there is a potential sort of cross-loading here, right, where there is a, non-ignorable sort of loading for factor 1 on cost, and the same thing here. There is a above 0.3 loading on depth for factor 2 that makes this kind of sort of complicated. There are some cross-loadings or complex loadings. So here we see that factor 1 is mostly depth and powder. It's like a snow condition factor. Factor 2 is mostly cost and lift, which you can think of as a resort factor. All right, so this is not just the snow, it's actually the resort itself. And both factors have complex loadings. But remember, this is just extracted, it has not been rotated. So let's rotate. Let's actually try to rotate them and see what happens. So factor extraction is usually followed by rotation, and by usually I mean it's always followed by, most of the time unless you have one factor, the factors are going to be really difficult to interpret without rotating. So we need to do that. So rotations usually increase simple structure and try to increase interpretability. The most common, at least as a first step, is varimax, which is an orthogonal rotation that tries to maximize variance for factors. So we're going to start with that first. Okay. So again, you don't need to memorize this. This is not something you're going to be given a test on, just to give you an idea of how this works. The way that we figure out how things need to be rotated is we need to figure out an angle of rotation. So the way this was done in the old days, and sort of even before my time, was that you could sort of plot out the points on a graph where the x and y axes were the factors. You can then try to figure out how far a factor needs to be rotated, and you can actually figure out the angle of rotation, and actually you can then figure out exactly how many degrees you want it to rotate. You can then plug that angle of rotation into this combination here of sine and cosine times that angle of rotation. It would then give you values to use that you can take these values, multiply them by these values, right? You take these values, multiply them by that transformation matrix here, these values, and then that would give you your rotated matrix. It would then and that would hold the commonalities constant, and it would rotate the variance for the factors around that 19 degrees of rotation. Now, people don't typically do this anymore. You know, I'm not sure actually what the algorithm is, but programs like SPSS, I think they just start to sort of rotate. They start to go in one direction. If the rotation is sort of successful, it's doing what it's supposed to do. Like in case of Varimax, it's starting to spread the variance out and maximize the variance on all the factors. It'll keep going until that stops and it doesn't do that anymore, and then the rotation converges. Or if it goes one way and it gets worse, it might go the other way and try to rotate until it gets, you know, tries to meet the criteria of the rotation. And in case of Varimax, it's trying to maximize the variance across the factors. So it's rotating variance from large factors to the smaller factors that have been extracted or retained. All right. Again, you don't need to know the sine, cosine, all this stuff. I'm not going to test you on those things. But the idea is that if you could have a question like, how do we convert a unrotated matrix into a rotated matrix? You take the unrotated matrix, multiply it by this transformation matrix, and that will give you then the rotated matrix. Okay, that's the sort of takeaway here. So we've multiplied our unrotated matrix by our factor transformation matrix, and we now get back these two factors where it's now increased the loadings for depth and powder on factor 1 and decrease the loadings for cost and lift on factor 1, making this a lot clearer that this is really a depth and powder factor with very little cost and lift in it. Where here, cost and lift are now very large. These are near zero, which means this is really a cost and lift or resort factor with very little depth and powder in it. So the factor 1 really is about snow, factor 2 is about the resort. And we can square these loadings. If I take and square this, if I can see where I'm at here, so I can take and square this and square that and add them together, that would equal this 0.970, right? So the commonalities are usually just square the loadings, add them up, and that's our commonality here. Square these two, you get the commonality there. Square those two, right? That's how the commonalities end up being estimated. If I square and add up this way, I get these sum of square loadings. This 1.994 tells me how much variability this factor is explaining in the total 4 units of variability. If you actually take 1.994 divided by 4, you get really rounds up to 0.5. If you do the same thing for 1.919, you get about 0.48. Okay. Then this right here is, if I added both of these up, the 1.994 and the 1.919, this is the total explained variance. So we're actually, of the 4 units total, we're explaining about 98% of the total variability. Okay. Going the other way around, this says proportion of variance, this says proportion of covariance. This is a table right out of Tabashka and Fidel's book. That could be a little confusing. The proportion of variance is the proportion of total variance. So this 0.5 is 1.994 divided by 4. The reason why this one goes up a little bit is proportion of covariance. This really should be proportion of explained variance. So the reason why this one goes up is because it's 1.994 divided by 3.915 instead of 4. So this is looking at what's the 1.994 relative to the total explained variance of 3.915, which is why this is a larger number than this, and this is a larger number than that by just a slight amount, because these have 3.915 in the denominator, while these have 4 in the denominator, but they're really close. Okay. So like it says here, commonalities are found on the factor solution by summing across, and we get this 0.97 value. Okay. So the way that's interpreted, 97% of cost, this first variable here, 91% of cost, 97% of cost, can be accounted for by factors 1 and 2 combined. So factors 1 and 2 I'm squaring and adding those together, tell me that we're explaining roughly 97%. We're explaining 96% in item 2, 99% in item 3, and almost 100% in item 4. Okay, so that's the amount of common variance that is shared for each item. This one, 97% is actually explained by the factors. 96, you get the idea. Okay, and in total, roughly 98% of the items. 90% of the variance in the items is being explained by the two factors. Okay, so we're covering 90% of the variance with just two factors, which is pretty good. So proportion of variance in a variable set accounted for by a factor is the sum of squared loadings for a factor divided by the number of variables. Okay, so the reason why we're dividing by 4, we're dividing by the number of variables, but it's not just we're taking an average. We're dividing by 4 because each item contributes 1 unit of variance. So this is the total amount of variance possible in this data set. So this is the amount of variance that factor 1 explains, or that accounts for. This is the total amount of variance. So about 50% of the variability, of the total variability, is explained by factor 1. That's why we're getting that 0.5 here. There. Okay. So this is talking about sort of fact, if I'm adding up this way, it looks at the sort of proportion of variance, and that's the sort of the proportion of total variance of 0.5 and 0.48, which is why we're dividing by 4, which is the total units of variance available in this data set because of the 4 items. Each item contributes 1. Okay. The proportion of covariance in a variable is accounted for by the factor. By a factor is the sum of squared loadings divided by the total commonality. So if I add up all the commonalities here, all the way across, you get 3.915. This is what I said a second ago. These second values here, 0.51 and 0.49, are a little bit larger because we're dividing by 3.915 instead of 4. So this is the total amount of common variance across all the items in these two factors. So we're getting those proportions down here by dividing by that number instead. Okay. Once we find the loadings, we can reproduce the correlation matrix. We can reproduce the correlation matrix, take our original correlation matrix, subtract the reproduced correlation matrix, and it gives you a residual matrix. So the residual correlation matrix is found by subtracting the reproduced correlation matrix from the original correlation matrix. And again, there's some matrix syntax if you want to check it out. I'm not going to go through it here, but it's there. It's available if you want it. And if you have any questions, you can actually go through that, and I'll be happy to help you sort of outside of this. But for a good factor solution, the residuals should be small, right? Meaning that you're trying to reproduce correlations, you want to get close. The closer you get to reproducing the actual correlations, the better you are at sort of covering all the relationships and all the patterns in your correlation matrix. So these should be pretty small. As a matter of fact, you want them to be 0. But it's not like they're going to be perfectly 0 because you're not retaining all the factors. The fewer factors you retain, there's going to be a bigger difference between the original and reproduced matrices. But you still want to get close, and the average residuals should be something like 0.05. And if that's true, then that's one way of thinking about your data is actually doing a pretty good job of reproducing, right? So on average, the residuals were 0.5 or lower. That's a pretty good way of looking at it. But you can also look at the actual residual matrix. And any place where you see values that are above 0.05 or any values that are getting larger, that tells you that there's some correlation or some relationship or pattern of relationships that your factors are not accounting for, and that's why there's a big residual for that particular pair of variables in that residual matrix. So it's a way of sort of pointing out where you might be missing some things or where your correlation matrix is not being explained very well. All right. So we talked about weight matrices before, these sort of the canonical weights or canonical coefficients or discriminant function weights, discriminant function coefficients. These are the same things, a factor weight matrix or factor coefficients. We can find them. These are the sort of slope-like values, the weights. Once we have our original correlation matrix, we have our loadings. If we just take our loadings and divide them by the correlations, which is why we're taking R raised to -1. This is the inverse of R times A. we'll get our factor weight matrix. And again, there's some matrix in the matrix syntax. You can actually play around with that and see that that actually does work out. And then you can use those weights. These are, I think, are the standardized weights. You can use those standardized weights then to compute factor scores. And actually, with the idea of being that if we can measure people directly on these factors, if we can actually bypass this whole process and just measure them directly, then this is what they would score on the factor if we could do that. So the factor scores then represent is a representation of the factors, the combinations of the items, into an actual composite score that so reflects the differences in the importance of the items. And in this case, it also helps to remove the error variance and that unique variance we talked about earlier. It removes that out and actually makes for a cleaner composite where the error has been removed and it's not being compounded by simply adding them all together. So these slopes are what are used to actually multiply by the items to get those factor scores so that every person has a score on factor 1, every person has a score on factor 2, creating two different composites, these sort of smart error, unique variance reduced sort of composites that should be cleaner and more psychometrically sound than just using a composite measure where you just add everything together. Okay. So once we have those standardized slopes, the standardized values, if we standardize our variables, take our cost, lift, depth, powder, standardize them, subtract the means, divide by standard deviations, turn them into z-scores, we can take those z-scores times these sort of beta, these weights, and create standardized factor scores. So once we have those, the standardized weights here, we can then use those to multiply by the standardized predictors, not predictors, there's no predictors in this, but standardized variables. So this is a matrix of standardized variables, cost, lift, depth, my tongue's getting tired here. Cost, lift, depth, and powder. If I standardize all those, I have a 4x5 matrix. Oh no, actually a 5x4. 5 people times 4 variables of z-scores that I can multiply by these coefficients to create factor scores for every person. Everybody would get then 2 different factor scores by doing this process. That's basically it, the way of sort of calculating factor scores. And then those factor scores can be used to predict other outcomes or to look at group differences on those factor scores. And they'd just be cleaner, at least psychometrically cleaner versions of a composite if you had just added them up. And it also gives you some reason, it gives you an operational definition for why those items can be combined, because it shows that they actually have substantial loadings. So it's both an operational definition and a way of sort of getting cleaner, smart composites from your data to then to score everybody on and use for further analysis. Okay. You can also estimate what each subject would score on the standardized variables, meaning that if you take their factor score times their loadings, we can then, this actually almost should have like like what their predicted score would be on, why am I putting an A there? I meant just a hat, not an A. So we can actually get their like sort of Z hat values. If we wanted to try to predict what someone would be based on their factor score and the loadings on the items, we can then get a predicted Z score for what everyone would score on the individual items based on their factor score. So it's sort of going in reverse. That's something you can do if you wanted to do that. And then you can look at sort of the residuals based on what they actually scored and what you predicted the score to be, and that's a whole other thing. But you could do that if you really wanted to see how well this model was predicting. How well the model is actually capturing the data. All right. Okay. So that's sort of what happens with sort of orthogonal rotation. It's actually fairly straightforward, even though it may seem weird trying to get these 19 degree of rotation and sort of doing that stuff. But at least theoretically, okay, so we're rotating factors, we're assessing them. It's not super complicated. With oblique rotation, the goal, oftentimes, oblique rotation will give you a cleaner interpretation of the items using the pattern matrix, but the way that we get there is a little more complicated. So in oblique rotation, the steps for extraction are taken. So the extraction part is the same, right? All the way up to how many factors you extract and all that stuff to get the unrotated matrix is the same, nothing changes. The variables are assessed for unique relationships between each factor and the variables, right? So we compute a pattern matrix, which is this matrix of like partial correlations between the items and factors, controlling for other factors. So it's like it says removing relationships that are shared by multiple factors. So we're trying to control for those overlaps between factors to compute unique relationships. What is the unique relationship between each item and a factor? The matrix of unique relationships is called the pattern matrix. And it's the pattern matrix that we typically will assess or try to interpret. The pattern matrix is treated like the loading matrix in orthogonal rotation in terms of trying to to go through and interpret which items go on what factor and all that kind of stuff. It's the pattern matrix we typically treat the same way as the rotated matrix in an orthogonal rotation. Once we have, so here the factor weight matrix and factor scores are found in the same way, right? Where the factor scores are used to find correlations between the variables. Okay, so we can actually compute the factor scores for the two factors. These are just the loadings. The loadings we already found. They're a little bit different than the ones we already found because these are the unique relationships. Go back a little bit. Go back to here for a second. So here it's like negative 0.086, negative 0.071, 994, 997. The values have changed. This is now the oblique rotation. Negative 0.079, negative 0.078, 0.994, 997. These aren't super different. Why? Because these factors aren't particularly correlated, so we're not getting a whole lot of change. But if they were correlated, then these values would start to change quite a bit because we'd be removing the overlap between the factors when looking at the correlations, and that would actually then, these would be more like partials, like partial correlations. Okay, so we can actually do the same process to find that. We can then find the weight matrices by taking our inverted correlation matrix times our loading or pattern matrix here to get our coefficients. That would be the same. We can compute our factor scores by taking our standardized variables times those weights to get factor scores, which we'd have here. So this is actually like the score for each person. This person would score 1.12 standardized value on the first factor and a negative 1.18 on the second factor. These will actually be their scores, their factor scores. Okay. Once you have the factor scores, once we actually have these numbers, we actually have their values, I can take these numbers and I can correlate them. I can find out how correlated is this factor and this factor, and it would give me the factors. So we can actually get a phi matrix, which is going to give me this. It's the factor score transpose times itself divided by 1 over n minus 1. You know, factor score, you can calculate the correlations between the factors. This is called the phi matrix. We saw that in the lab. It's that factor called the factor correlation matrix. It tells you the degree to which the factors are actually correlated. And so here's those factor scores times themselves times this 1,4 divided by 4, and we get that the correlation matrix here 1, negative 0.01, negative 0.01, and 1. So the reason why we're not seeing a big change in the actual loadings is because these factors are correlated at negative 0.01. They're essentially 0. They're not correlated. So doing an oblique rotation on this particular data doesn't make a lot of sense because they're not correlated. It's not really giving us any more information, but this is how it would be done if you needed to do it. So once you have the pattern matrix, the problem with the pattern matrix is you can't really use that to compute things like commonalities or other portions of the data. So you actually need to take your pattern matrix times your factor correlation matrix to get your structure matrix. Here's your structure. Here's the pattern times the factor correlation matrix to give you your structure matrix. So the structure matrix is, you can interpret this as the 0 order correlations between each item and the factor, with the factors correlating, that means there's some overlap and redundancy in these correlations, which makes it sort of more difficult to interpret. This particular example is not a good one because, it's still, these are large, these are near zero, these are near zero, these are large. So you could probably interpret the structure matrix as easily as you could the pattern matrix, but that's definitely not going to be true for most data when the factors are actually correlated. These numbers are going to vary quite a lot from these, and I think we saw that in our lab when the pattern and the structure matrix was a mess. There were just numbers all over the place, and the pattern matrix came back very clean and very nice and neat. And that's actually fairly typical when you have correlated factors. Doing an oblique rotation is actually going to help to clean up the interpretation of those factors, with the structure matrix is not going to help you very much. The structure matrix, though, is necessary because with the oblique rotation, if we want to be able to reproduce the correlation matrix, I can't just take, so going back to our orthogonal rotation, my reproduced matrix was found by simply, back a little farther, I could reproduce my factor matrix here by taking my loading matrix times my loading matrix transpose to get my correlation matrix. I could reproduce it because there's just one factor matrix and one rotated matrix. I can use the loading matrix to do that, and I can reproduce my correlation matrix. All right. With oblique rotation, you can't just take your pattern matrix times your pattern matrix, and you can't take the structure matrix times the structure matrix transpose. You can't do that to reproduce the correlation matrix. To get a reproduced correlation matrix, you have to take your pattern matrix times your structure. C is a structure matrix, times your pattern matrix, which is this, right? Take your structure matrix times your pattern matrix, so transposed, and that's how you get your reproduced matrix. So that's what I'm saying, where oblique rotation is oftentimes more useful to get a cleaner pattern of relationships in your loadings, so you can actually interpret it. But it just requires more work to actually do things like get a reproduced matrix or calculate commonalities and other things. Are just a little more complicated because it requires more steps and there's more pieces. Instead of having one extracted matrix and one rotated matrix, I now have an extracted matrix, two rotated matrices, and then a factor correlation matrix. So there's just more things to interpret, more complexity, but sometimes that added complexity helps you to get a cleaner picture of what's going on in your factors and your items. So it's worth the sort of trade-off there. All right, so that's a super skimpy sort of review, a lot of this stuff in terms of how things are done. I want you to go through, think big picture about things that, in an oblique rotation, the reproduced matrix requires both the pattern and the loading matrix, right? The structure and the pattern matrix. Where in a orthogonal rotation, it's just the loading matrix times itself to reproduce the matrix. So just things like that. Think bigger picture. You don't need to memorize equations. You don't need to know how to multiply the matrices around. It's just an idea of sort of getting the bigger picture of how this stuff is done. So the last few things I want to make sure I mention is like what else? Right, well, how many factors do you extract? The default in SPSS, and I imagine other programs as well, is to extract all factors with eigenvalues greater than 1. So if you extract all values greater than 1, this is something called the Kaiser criteria, which I have here, right? This is the default in most programs, that if you take and only keep the eigenvalues that are greater than 1, that's the Kaiser criteria that is applied in SPSS, right? And the logic there is that if each item contributes 1 unit of variance, then your factor should do better, should be doing as good as, at least, or better than 1 item. If it falls below 1, it means your factor is explaining less variance than any single item is explaining or contributing. Therefore, it's not even as good as 1 item. So that should, sometimes people think of it as a sort of minimum criteria. I've seen another argument that extract all factors with non-negative eigenvalues. I've never seen a really good application of this, because most of the time, as you'll see, the eigenvalues, these are all non-negative. So that would mean extracting all 12. So that's not necessarily a good criteria, but you will come across that sometimes. Another thing that gets put out there all the time in textbooks is to look at the Scree plot, and I mentioned that in lab. There's another sort of super confusing use of things. You're supposed to separate out like what are the real factors here from the sort of noise that's sort of cycling down through the leftover variance. It's called a Scree plot because if you go hiking or something, you come across a cliff, and on a cliff, you're hiking, right? Think about a cliff, right? Here's a cliff, right? It's got, maybe there's like a tree or something sticking out of the cliff, and right, it's down here, and then there's the ground. Okay, at the bottom of any cliff, you're going to have a pile up of a bunch of like pebbles and stuff all down here that piled up from breaking off of the cliff face and sort of coming down. So you get this sort of junk down here, and this junk is called scree. It's like the rocks and pebbles and twigs and things that have sort of fallen from here and sort of piled up at the bottom of a cliff. In the same way, the Scree plot is supposed to be able to help you tell the difference between the cliff itself and the scree, right? So what is scree and what's really cliff? And the way that's typically done, do I have a straight edge of some sort that I can use? Let's see, what do I have? I'll use this, I guess. If we take and try to find a straight edge value, right? If I go, this is not quite long enough, but if I were to go here like that and try to draw a line that was straight across here like this, so we connected all the points and continue that straight line here. I'm not doing a very good job because I can't really tell, but let's see. Alright, this is not perfectly good, but alright, so I didn't do that very well. Imagine the line is actually a little thicker, maybe. Might actually help. Alright, so here, here is a straight line that because oftentimes when the values start to cycle down through sort of residual leftover variance, it starts to cycle down fairly consistently. Like it's just, you're explaining a little bit more error. It's just, more noise being explained. It sort of cycles down. So you can see that each time, the reduction in error is sort of fairly constant all the way down. It just sort of cycles through. So if you can actually identify where that is, anything then that's above that line, right, would be considered sort of a true representation of a factor. That this is really the cliff face. Here's your scree down at the bottom, and you're trying to sort of sift through that. The Scree plot's supposed to be able to do that for you. It's just oftentimes it's misleading at best, super subjective, and and most of the time, really, you're going to come back with the same conclusion that you did before anyway. So here, in this case, this can't be this is something with 12 items, so it's not the cost and lift one. This is 12. This is some example with 12 different items. It's not the cost, lift, depth, powder, because I would only have 4. This has 12 items, and it's telling us that we should retain 1, 2, 3 of them. And what you find with that, when you go to retain, go back a second, go back to here. There are 3 factors that are above 1, which means if I conclude with the Scree plot that there are 3 factors that I'm going to retain, it's telling me the same thing the Kaiser criteria does. Right? It hasn't given me any more real information. Now, oftentimes that's what's going to happen. The Scree plot's going to tell you about bring you to the same conclusion that the Kaiser criteria, the default criteria, will anyway. Every once in a while you'll get, like if I was to be really super strict about drawing a straight line here, what would happen is this particular point here actually falls sort of above the line. So we identify that this is now sort of a viable viable factor, then instead of being 3, instead of extracting 3 like this says, the Kaiser criteria says to keep 3. Well, I can use the scree plot instead and decide to extract 4. What you see right here is the sum of square loadings for these items are below 1 now. It actually looks like pretty crappy items. Okay, but then you rotate, and it's possible that these 2 items, all of a sudden this item comes back above 1, this item stays below 1. So now you have to decide whether or not it's worth keeping this one, even though after rotating it's still doing a pretty crappy job. So the scree plot is, if you something you want to refer to, that's great, but you still got to go back and sort of look, what does it actually mean to retain this 4th factor, if that's what the scree plot tells me. It actually doesn't seem like it's doing a whole lot of good in the end when, after rotating, it's not really doing a whole lot. This was, looks like a Varimax rotation, and Varimax wasn't able to maximize this variance much of all. I mean, it brought it up higher than here, but it's still doing a fairly, it's not even doing 1 unit after Varimax has sort of funneled variance to it. So sometimes the scree plot's not, it's sometimes good if you're really trying to explore and figure out what might be going on in your data set. Check out the scree plot, look at it, and see if it can give you some different ideas of number of factors to try. But in the end, you got to look at what's useful, what's actually being explained well enough to sort of want to keep it. And there's nothing in here, not in the initial eigenvalues, not in the extracted eigenvalues, and not the rotated sum of square loadings here, but to tell me that that item is sort of viable or worth sort of keeping. But other people might argue that even if it has a small sum of squared loadings or something like that, that separate subfactor may be useful. It may predict things differently than the other factors. And maybe if I went to an oblique rotation, all of a sudden this now would be revitalized and be a much larger number. So even when you get to this point, the option could be, well, either drop it, or I try to go to a different rotation to see if it actually fixes the problem too. That's why factor analysis is one of those things where you're never going to run it just one time and get an answer. You're going to try different things. It has this sort of exploratory feel to it because you're trying to figure out what's actually going on. And that's why I mentioned too, it's sort of more art, or as much art as it is science. There's all the mathematics behind it, but there's all kinds of stuff to play around with. That's the art part that you have to sort of learn and get used to and be accustomed to, sort of how to interpret how things change as you change different aspects, like the number of factors to extract, the kind of rotation to use, those kinds of things. All right, last piece, and the part that makes this even more sort of an art form comes down to, once you sort of extract factors and rotate them and all kinds of stuff like that, how do we make sense out of them? So yes, we know, we can tell, oh, these items load on factor 1, these items load on factor 2, which gives us some information about where items should go and where they shouldn't go. But what are the factors? What are they actually doing? So if you have a bunch of items measuring depression and they come back as one factor, you can say, okay, well, these items measure depression. But as you're looking at subscales and various things, you have to look at the item content somewhat to figure out what's making up that factor. So how do you know, okay, so that's this question down here, I sort of skipped one. How do you interpret factors? That's a really good question, and that's where the true art comes in. You gotta look at the item content, see why the item content across items are being shared, and try to figure out what latent metaphysical thing, what kind of construct could be driving those responses to be similar. And that's really what it comes down to. You may have to do some outside the box thinking. You may have to really use your brain to try to figure out exactly how items go together and why they're being put on the same factor. And it doesn't always line up the way you think it might. And you have to be sort of careful with interpretation, making sure not to force things that don't really belong together. Sometimes they, even though you might have thought an item captured one aspect of a complex sort of construct, it may be really better at something else, so that's why it's not lining up the way you thought. How do you know when a factor structure is good? Well, for exploratory factor analysis, there's not a whole lot of concrete ways, right? You can argue lots of different ways, lots of different things. That, you know, the eigenvalues or the sum of squared loadings is high when you rotate. That the items are, that you got simple structure. There's all kinds of things you can argue that make factors good or bad. But most of all, the factors should make some kind of sense. Right? You should be able to interpret them. It should make sense according to whatever theory sort of drove the creation of the questions in the first place. And you wanted to have relatively simple structure. So a factor analysis is good when the structure is as simple as it can be, and the factors make sense. And I would even add to this that the factors have some use, that they can be used to predict other things, that can be used as outcomes, that they actually have, they have a useful sort of purpose to them. If they have those things, then it's pretty good. Then your factor structure is probably pretty good. Doesn't mean that it's the only factor structure that could have been found. And that's sort of part of the struggle with this, is that you could factor analyze, especially larger data sets, a few different ways, and all of them seem perfectly viable. And it's really going to be based on your theory or something that's going to really lead someone to believe one way or the other in terms of what factor structure really is the right structure. Until you go into sort of confirmatory factor analysis, where there actually are tests like goodness of fit tests that can tell you whether or not your model sort of fits your data, your factor structure fits your data. You're not going to get a whole lot of satisfactory answers about how do we know when a factor structure is good. When we go into 534 in the fall, for many of you, we will talk about confirmatory factor analysis and how you can use goodness of fit tests and things like that to tell you if your factor structure seems like it's a good fit for the data that you have. But until then, it's sort of it's really more or less your factor structure is good when you can argue that it's good, and use the patterns of the loadings, use the item content to argue that it actually makes sense, and that it is a useful sort of viable structure for that data set, which is not very. So it's sort of unsettling. There's no like hard rule about it. We're so used to significance is 0.05 or less. Very definitive answers, and this doesn't have that. That's why there's a lot, sort of an art to it. All right, I think that's it. So that's all we're going to talk about for factor analysis. If you have questions, please send them my way. Otherwise, this wraps up factor analysis and really wraps up the whole semester. I hope you all enjoyed, as much as you can, enjoyed the sort of multivariate stats. And despite the fact that we sort of had to transition over to this sort of online method and stuff, I hope I was able to keep it interesting and keep the sort of quality of instruction sort of high, even though we ran out of time and everything was sort of crazy, a little frantic sort of triage mode since the sort of lockdown, stay-at-home order started. But I did what I thought was the best I could, and I'm coming in using this sort of lightboard thing, hopefully to sort of keep it at least engaging. So I hope that worked. I hope it wasn't sort of a waste of time to sort of do all this. But so all right, have a good one. Take care.